Hi friends, welcome to KNS One Shot series. Myself, I am Satish, Faculty of Chemistry. Today we are going to discuss P block elements. You have already discussed the first year P block elements, introduction, group 13 and 40. Today I am going to discuss second year P block elements, that is group 15 onwards, group 15, group 16, group 17 and group 18. Let us have a look on group 15 elements. See, group 15 elements are also known as nicogens. What do you mean by nicogens? Nico means poison. Gen means producing. Nicogen means poison producing elements. And which are the members of group 15 elements? Nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. These are the members of nicogen family. Before going to study the physical and chemical characteristics, we should have an idea about their general features: electronic configuration, atomic radii, ionized enthalpy, and electronegativity. So first, let us look at the valence electronic configuration. These group elements have 5 valence electrons. 5 valence electrons. These 5 valence electrons are arranged in Ns and the Np orbitals of the valence shell. Look at the electronic configuration: Ns2, Np3. Ns orbital is completely filled and the Np orbital is half filled. So this electronic configuration is exceptionally stable. Keep in your mind this electronic configuration: half filled, completely filled orbital. So it is highly stable. Then coming to atomic radii. As we move down the group, atomic radii increases because number of shell increases. So atomic radii: nitrogen less than, phosphorus less than, arsenic less than, antimony less than, bismuth. So there is no abnormality. Then coming to ionization enthalpy. These elements have high ionization enthalpy than group 14 or group 16 elements because their last electron is in stable electronic configuration, p orbital, half-filled p orbital. So it is very difficult to remove stable electron from stable half-filled configuration. So their ionized enthalpy is very high. Then in the group, as we move down the group, as the size increases, so ionization enthalpy again decreases. So down the group, ionization enthalpy decreases. You can see the order on the board. Again, coming to electronegativity, nitrogen is highly electronegative. Then down the group, electronegativity decreases. So these are the general characteristics of group 15 elements. Coming to physical properties, here nitrogen and phosphorus are non-metals present in this group. Arsenic and antimony are metalloids. Bismuth is a typical metal. And physical state பார்க்கும்போது nitrogen is a gas. And phosphorus, arsenic, antimony, bismuth are solids. Bismuth is a metal, so it is a solid. Phosphorus is a solid. Nitrogen is a gas. What is the reason? Nitrogen can form stable p-pi multiple bonds. பாருங்க, இந்த molecule N2 molecule nitrogen ஒரு sigma bond இருக்கு, ரெண்டு pi bond இருக்கு. இந்த ரெண்டு pi bond p-pi bond தான். p-pi bond. அப்படின்னா இந்த nitrogen p orbitalum இந்த nitrogen p orbitalum யூஸ் பண்ணி pi bond form ஆகும். So that pi bond is highly stable, strong and stable. So nitrogen exists as N2, a small molecule N2. And a phosphorus exists as P4 molecule because its p orbital is diffused, bigger orbital. So it cannot form effectively stable bond, pi bond. As a result, phosphorus cannot form p-pi multiple bond. அதனால phosphorus single bond மட்டும்தான் form ஆகுது. So phosphorus molecule exists as P4. Arsenic molecule exists as AS4. Okay. So nitrogen exists as N2 and phosphorus exists as P4. P4 molecule is large molecule. So van der Waals force or London force is very strong. So it exists as solid. Nitrogen small molecule, so force of attraction is very less. So it exists as gas. So N2 is a gas, P4 is a solid. Then coming to allotropy. What is allotropy? Allotropy means one element can exist in different form. That is called allotropy. Except nitrogen, all other elements can form allotropy. For example, phosphorus. Phosphorus can show allotropy. It can form white phosphorus, red phosphorus, and black phosphorus. Black phosphorus is a stable allotrope of phosphorus. Then, boiling point, as we move down the group, boiling point increases, and the melting point from nitrogen to arsenic increases. Then, arsenic to bismuth, it decreases. Okay, coming to oxidation state. What are the important oxidation states of this group? In all the P block groups, there is one common oxidation state. It is called a group oxidation state. How the common oxidation state is achieved? If all the valence electrons are given for bonding, these elements achieve common oxidation state or group oxidation state. For group 15 elements, if all the 5 valence electrons given for bonding, they acquire +5 oxidation state. In addition to that, this -3 oxidation state is also stable. After getting 3 electron, they acquire noble gas configuration. Okay, so there is a group oxidation state. There is negative -3 oxidation state. In addition to that, there is a +3 oxidation state. What is +3 oxidation state? How it can happen? In +1 session, you studied that there is inert pair effect as we move down the group in any group of P block. See, nitrogen to bismuth, as we move down the group, the stability of group oxidation state decreases. And the stability of an oxidation state 2 unit less than group oxidation state increases. That is called inert pair effect. So, nitrogen, phosphorus, arsenic, antimony, bismuth, nitrogen is stable in group oxidation state, +5. But bismuth is stable in +3, 2 unit less than group oxidation state due to inert pair effect. Okay, so nitrogen is stable in +5 and bismuth is stable in +3. In any situation, bismuth form +5 oxidation state, it reduced to bismuth +3. So this process is called a reduction. +5 converted to +3. It is a reduction. So it can act as an oxidizing agent. So bismuth +5 can act as an oxidizing agent. Okay. Then nitrogen can exhibit all the oxidation state from -3 to +5. So all the oxidation from +1 to +4 undergo disproportionation reaction. That is self-oxidation and reduction, simultaneous oxidation and reduction in acidic medium to get a stable +5 oxidation state. That is a very good example is 3HNO2 gives HNO3 plus 2NO plus H2O. So here, HNO2 nitrogen is +3 oxidation state. It is converted to stable +5 and another oxidation state +2. So this is a disproportionation reaction. Then coming to phosphorus also the same thing happened. Phosphorus also some oxidation state +1 to +4 oxidation have tendency to undergo disproportionation reaction. A very good example is H3PO3. H3PO3 means phosphorus acid having +3 oxidation state of phosphorus converted to +5 oxidation state and -3 oxidation state. So this is also a disproportionation reaction. Then anomalous behavior of nitrogen. See, in P block elements, an important concept is anomalous behavior of first member of each group. What are the reasons for the anomalous behavior? These first element have small size, small atomic size, high electronegativity, high ionization enthalpy, absence of d orbital, high polarizing power. So here also nitrogen shows some abnormal behavior from the rest of the family members. We can look at some example for anomalous behavior. First one, maximum covalency of nitrogen is 4. See, nitrogen can show +5 oxidation state, I told you, but it cannot show 5 valency because it do not have d orbital. Nitrogen has electronic configuration 2s2, 2px1, 2py1, 2pz1. So these 3 p orbitals can be utilized for hybridization and also covalent bond formation. And s orbital also can be used for hybridization. And the s orbital contain one lone pair electron. So this lone pair electron can be donated to any Lewis acids. So there is a coordinate bond it can form, nitrogen can form. So nitrogen can form 3 covalent bonds and 1 coordinate bond. So altogether 4 valencies. Then coming to the second point, nitrogen has unique ability to form multiple bond with itself. See, nitrogen can form multiple bond with itself. N triple bond N. Similarly, similar size with a similar size the element. Carbon triple bond N. So nitrogen formed a stable p-pi bond with the oxygen, then carbon, similarly with itself, with a nitrogen, another nitrogen atom. But other elements are not stable in forming p-pi multiple bond. These bonds are pi bonds are p-pi multiple bonds. While other elements can form d-pi or d-pi multiple bonds because their d orbitals are more projecting outward. For example, R3p double bond O, R3, this molecule. See here, 3 alkyl groups are there. 3 alkyl groups are there. It is attached to phosphorus and there is a double bond. 3 alkyl group, out of double bond, one bond is sigma bond. So there are 4 sigma bond. 4 sigma bond and 1 pi bond. So phosphorus utilized all the s and p orbital for forming sigma bond and hybridization. And 1 orbital is there for pi bond, that is d orbital. So it is a d pi p pi multiple bond. So this double bond is a d pi p pi multiple bond. Then third anomalous behavior of nitrogen. See, it cannot show allotropy. What is the reason? That word allotropy or catenation is dedicated for carbon. Carbon can form single bond. As a result of carbon-carbon single bond catenation property, it can form long chain. Then cyclic structures. Nitrogen cannot form long chain or cyclic structures because nitrogen single bond is highly unstable. Nitrogen single bond and also nitrogen double bond also unstable. What is the reason? See, if nitrogen single bond is formed, there are other non-bonding electrons. They will repel each other. Nitrogen has small size of the nitrogen atom coming closer as a result of bonding, and the non-bonding electrons will repel each other, so that bond will break easily. So nitrogen cannot show allotropy. Maximum nitrogen can form triple bond N, triple bond N with a very high bond enthalpy of 946 kilojoule per mole. So very high bond enthalpy of N triple bond N. So nitrogen is chemically inert. At room temperature in atmosphere, nitrogen is not reactive. What is the reason? Because of the triple bond between N and L in a N2 molecule. Okay, coming to chemical reactivity, let us look the reactivity towards hydrogen. These elements react with hydrogen to form hydride of the type TH3. Nitrogen form NH3, phosphorus form PH3, arsenic from ASH3, antimony from SBH3, and bismuth from BaH3. And what are the characteristics of these hydrides? For NEET examination, the order is very, very important. The order can be asked. So, very, very important topic we are discussing now. Stability of this hydride. See, NH3, then BaH3. Nitrogen is small size. Bismuth is large size. And then nitrogen will form bond with the hydrogen. Then bismuth can form bond with the hydrogen. So, large size atom form bond with the small size atom. That bond is not sufficiently strong. It can easily break. NH bond is strong, BAH bond is weak. So, BAH bond can easily break to give bismuth and hydrogen. So, the order of stability is NH3 greater than, PH3 greater than ASH3, SBH3, and BAH3. Then, after breaking this bond, bismuth BH3 can give bismuth and hydrogen atom. So, removal of hydrogen. What is the removal of hydrogen? Removal of hydrogen is oxidation. The mole of hydrogen in oxidation. So that species can act as good reducing agent. So which one is good reducing agent? BiH3 is the strongest reducing agent among the hydrates of group 15 elements because BH3 can easily break the bond, easily give hydrogen. Okay. Again, Lewis basic character. Lewis basic character. See, Lewis base means a lone pair donor. We know that all these hydrates contain one lone pair electron. It can be donate. Which hydrate can easily donate lone pair electron? That depends on the electronegativity of the central atom. Consider NH3. Nitrogen contains a lone pair of electron. See, here nitrogen is more electronegative than hydrogen, so all the electrons are coming towards nitrogen atom, thereby increasing electron density around nitrogen atom. So, electron density is very high and it is highly unstable. So, this lone pair can easily donate. Whereas last member Ba, bismuth hydride. Bismuth is least electronegative. It's a metal. So, it is electropositive. So, it needs electrons. So, it will not, the electronegativity is very, very less. So, it cannot, the electron density around bismuth is very less. So, lone pair cannot donate. Okay. Then bond angle also can be explained on the basis of electronegativity. So, this electron density around the nitrogen is very, very high. Very, very high. So, that the repulsion between bond pair is very, very high. So, bond angle very high. So, Lewis basic character and bond angle of NH3 higher than PH3, ASH3, SDH3 and BiH3. One more property is you have given, that is boiling point. Boiling point, as the size of the compound increases, intermolecular force of attraction increases. As the size increases, intermolecular forces, that is van der Waals force, London force increases, so boiling point increases. But here there is an abnormality of NH3. Ammonia form intermolecular hydrogen bonding. As a result, ammonia boiling point is higher than ASH3 and PH3. Okay. Then, coming to the reactivity towards oxygen, these elements form two types of oxide, E2O3 and E2O5 based on oxidation state. E2O3 means +3, E2O5 means +5. And oxides of nitrogen and phosphorus are acidic in nature because you studied. Chinna class la ninga padichirukku. Or non-metallic oxides are acidic. Metallic oxides are basic. See, metals oxide of bismuth is basic. Then metalloid oxides, they are amphoteric in nature. And oxides in which element having lower oxidation state, less acidic than higher oxidation state. See, acids in the N2O, NO, N2O3, N2O5, N2O4. See, here nitrogen exhibits a +1 oxidation state. Here +2, here +3, here +4, and here +5. Oxidation state of element increases. Positive oxidation state increases. Lewis acidic character increases. Acidic character also increases. Okay. Then reactivity towards halogens. See, here also there are two types of halides, trihalides and pentahalides. Trihalides, in which +3 oxidation state of central atom, pentahalides, +5 oxidation state of central atom. Nitrogen can form only trihalide because absence of d orbital. Nitrogen maximum valency is 4. So nitrogen cannot show pentavalency. Nitrogen can form only trihalides, NF3, NCl3, NBr3, Ni3. Okay. Out of which stability பார்க்கும்போது NF bond is more stable because nitrogen have 2p orbital, fluorine have 2p orbital, their effective overlapping will take place. So strong, stable bond is formed. So NF3. But NCl3 பார்க்கும்போது nitrogen's 2p orbital, but chlorine 3p orbital. Size increases. Chlorine, bromine, iodine. As the size of halogen atom increases, the effective overlapping will not take place. So stability decreases. So NF3 greater than NCl3 greater than NBr3 greater than Ni3. Then pentahalides are more covalent than trihalides. You studied Fajan's rule in +1 classes. Pentahalides in which plus 5 oxidation rate of the central atom, PCl5, then PCl3. PCl5 means plus 5 oxidation state, PCl3 na plus 3 oxidation state. Pentahalides. You know what is Fajan's rule? Higher the positive oxidation state of the central atom, higher will be the polarizing power. As a result, higher will be the polarization. Then the bond covalent character will be very high. So pentahalides are more covalent than trihalides. PCl5 can exist as a trigonal bipyramidal structure, TBP, with the sp3d hybridization. What is the structure of PCl5? Trigonal bipyramidal. Trigonal bipyramidal structure of PCl5. This is the trigonal plane. Bipyramidal. Trigonal bipyramidal structure. And axial bonds are longer than equatorial bonds you studied in hybridization topics. Okay. Then we are going to next group. Group 16 elements. They are called chalcogens. So group 15 elements are called nicogens. Group 16 elements are called chalcogen. Why such a name, chalcogen? Chalco means mineral. Gene means foaming. Mineral forming elements, ore forming element. Most of the minerals or ores obtained from earth crust are containing either sulfur or oxygen. So sulfur and oxygen are members of this family, hence the name chalcogens. Members of the family are oxygen, sulfur, selenium, tellurium, polonium, livermorium. These are the members. And let us look at the general characteristic. What is the general electronic configuration? Ns2 Np4. Ns2 Np4. So 6 valence electron, it can be accommodated as Ns2 Np4. And atomic radii also there is no abnormality here. As we move down the group, size so increases. Oxygen less than, sulfur less than, selenium less than, tellurium less than, polonium. Then coming to ionization enthalpy. See, ionization enthalpy, it is lower than group 15 elements. What is the reason? Group 15 elements have stable half-filled configuration. Here there is no special stability for this electronic configuration. Here look at the first ionized enthalpy of oxygen. First ionized enthalpy of oxygen is less than that of nitrogen. But second ionized enthalpy of oxygen is higher than nitrogen because second electron should go from oxygen stable half-filled configuration. If these elements remove one electron, they acquire stable half-filled configuration. Okay. Coming to electron gain enthalpy. What is electron gain enthalpy? Energy release when an isolated gaseous atom accepts an electron. What is that? What is the case of electron gain enthalpy in this group? You can look at here. In periodic table, already you studied electron gain enthalpy decreases down the group. But here there is an abnormality you can see. Oxygen electron gain enthalpy is lower than rest of the family members. Why? Because oxygen have very small size. If it accepts one electron, there will be interelectronic repulsion. ஏற்கனவே தார் எலக்ட்ரான்ஸ் இருக்கு இன்னொரு எலக்ட்ரான் கூடி வந்துடும் போது interelectronic repulsion அதிகமாயிடும். So release less energy. That means one electron accept பண்ணும்போது electron கொஞ்சம் unstable ஆயிடும். Not fully, கொஞ்சம் unstable ஆகி மாறும். ரெண்டு எலக்ட்ரான் வந்துடும் போது ஆக்சிஜன் octet ஆயிடும், stable ஆயிடும். So electron gain enthalpy of oxygen is less than that of sulfur, selenium, tellurium, even polonium also. Okay. Then last one, electronegativity, you know, down the group, it decreases. Oxygen is highly electronegative in this group. You know that in periodic table, second most electronegative element is oxygen. 3.5 is the electronegativity according to Pauling scale. Then, coming to physical properties of chalcogens. Oxygen and sulfur are non-metals. Selenium, tellurium are metalloids. And the last element, polonium, is a metal, but it is highly radioactive. Polonium is a radioactive metal with a half-life period of 13.8 days. Okay. And all these elements form allotropy. In the nicogens, group 15 elements, except nitrogen, others form allotropy. In group 16, all elements form allotropy. So, which is allotrope of oxygen, O2 and O3. Dioxide and ozone are the allotrope of oxygen. Sulfur forms so many allotropes. Monoclinic sulfur, rhombic sulfur, cycloesic sulfur. So a lot of allotropic forms sulfur can form. And melting point, boiling point increases down the group. As usual, increases down the group. And one abnormality we can say the large difference between melting point and boiling point of oxygen and the sulfur. See, there's here also the same question. Nitrogen and phosphorus. Nitrogen acts as N2, N2 acts as gas, phosphorus acts as solid. Same question ingame varala. Oxygen acts as gas, sulfur acts as solid. The same reason. Oxygen can form P pi multiple bond. So oxygen can exist as P pi multiple. Oxygen can exist as O2 because of P pi multiple bond. In group 15 elements, nitrogen can form P pi multiple bond. So nitrogen can exist as N2. Phosphorus, it cannot form P pi multiple bond. So it can exist as P4. Only sigma bond. Only single bond. Adhe madri sulfur. Sulfur is octa-atomic. 8 atoms are there in one molecule of sulfur. And all the atoms, all the sulfur atoms form single bond. Because it cannot form P pi multiple bond effectively. Because their p orbital is diffuse, large size. Okay. So O2 molecule, between one O2 molecule and one O2 molecule, there is weak van der Waals forces, but large sulfur S8 and S8, strong van der Waals force. So sulfur exists as S8 solid and oxygen exists as O2 gas. Okay. Coming to the oxidation state. I told you that, in every group, there is a common oxidation state or group oxidation state. In group 16 element, +6 is the common or group oxidation state of chalcogen. +6. But as we move down the group, inert pair effect become more predominant. +6 become unstable. So, group first member, oxygen cannot show +6 oxidation state. Oxygen cannot show valency more than 4. And sulfur can exhibit +6. Sulfur, selenium, tellurium, polonium. But tellurium can exhibit +4 oxidation state. Tellurium is stable in +4 oxidation state because of inert pair effect. Polonium is a radioactive element, so I'm not writing anything on polonium. And tellurium is stable in +4. Sulfur is stable in +6. In addition to this, some other oxidation state also they can exhibit the +4, +2 and the -2. +2 and -2 also they can exhibit. -2 have one importance. If they accept 2 more electron, they acquire noble gas configuration. If 15 elements accept 3 electron, they will obtain noble gas configuration. Here, if group 16 elements, 2 electron accepted, they will acquire noble gas configuration. Okay. So these are the point regarding oxidation state. Then coming to anomalous behavior of oxygen. Anomalous behavior of oxygen, because of the first member, being the first member, it is small size. It has high electronegativity, high ionized enthalpy, absence of d orbital. So it can exhibit anomalous behavior. Some examples are given. Water is a liquid while H2S is a gas. Water is a liquid because of intermolecular hydrogen bonding. See, in ammonia is also liquid. Ammonia is a liquid because intermolecular hydrogen bonding. Water is a liquid, intermolecular hydrogen bonding. Intermolecular hydrogen bonding is strong in water as compared to ammonia because oxygen, hydrogen, electronegativity of oxygen higher than nitrogen. Then H2S, other elements, other hydrogen group 16 hydride do not form hydrogen bonding, so they exist as gas. So H2O is a liquid due to intermolecular hydrogen bonding, and H2S is a gas. There is no hydrogen bonding in H2S. And maximum covalency of oxygen. Theoretically, maximum valency is 4 because of 4 orbitals are available in its valence shell. 2s2, 2px2, 2py1, 2pz1. So 4 orbitals are available in the valence shell of oxygen. Therefore, 4 valency theoretically we can predict it. But actually, it can show always 2 valency. 2 covalent bond it can form. For example, water, H2O. 2 covalent bond can form. In addition to two covalent bond, one coordinate bond also can form. So maximum 3 valence is practically possible for oxygen. In coordination compounds, you studied water as a ligand, oxalate as a ligand. All these cases, oxygen can donate a lone pair of electrons. Then coming to chemical reactivity, here also reactivity towards hydrogen first. Reactivity towards hydrogen. All these elements form hydride of the type H2E, H2E, H2O, H2O, H2S, hydrogen sulfide, water, hydrogen sulfide, hydrogen selenide, hydrogen telluride, hydrogen polonide. Actually, hydrogen polonide is radioactive, so we can avoid H2PO for our studies. Stability in that case, we can avoid H2PO. Theoretically, we can write H2PO, but practically we know that H2PO is radioactive. So as we move down the group, stability of hydride decreases because oxygenum, hydrogenum, similar the small size, so they can form effective bond. But last remember, tellurium and hydrogen, hydrogen small size, tellurium and hydrogen. So this bond is a very weak bond, and this is a strong bond. As we move down the group, size of the central atom increases. So central atom hydrogen bond strength decreases. So it can easily remove hydrogen. It can easily break the bond. So stability, the same as in the case of group 15 hydride. From first member to last member hydride, stability decreases. Again, reducing character. There we studied, group 15 also we studied. First stability, second, which one can act as strong reducing, which one can easily give hydrogen atom. H2S, H2SC, H2T I am taking. Why I avoided water? See, water can act as oxidizing agent and reducing agent. So water we are not taking in this case. So by comparing all these three cases, down the group, H2T can easily remove hydrogen. H2T can easily remove hydrogen. So that bond can easily break. So it can act, easily remove hydrogen means it can readily undergo oxidation. So it can act as reducing agent. So H2T is strong reducing agent, H2SC, then H2S. Again, coming to bond angle. See, bond angle in group 15 hydride, I told you the same reason. Electronegativity of the central atom decreases, bond angle decreases. What are greater than H2S greater than H2C greater than H2T greater than H2PO? That is the order of bond angle because electronegativity of central atom decreases. So in group 15, group 16, their hybrids bond angle decreases down the group. Then boiling point, melting point. In group 15, I told you boiling point. I told you. Down the group, boiling point increases because intermolecular force of attraction increases. Van der Waals force, or more clearly, London force increases down the group. Okay. There are an abnormality of ammonia because it can form iron bonding. Here, the number one is water, H2O. First member hydride is highest melting and boiling point because of the strong intermolecular hydrogen bonding. Water has high boiling point, high freezing point because of strong intermolecular hydrogen bonding. Again, last one more character, acidic character. Through 15 hydride, basic character, Lewis basic character discussed. Here, acidic character we are discussing. More polar bond. H element bond is more polar. Here also we are avoiding water. What is the reason? Because water can give H plus and OH minus ion. So we are avoiding water as compared other elements, other hydrates. Which one can easily donate H plus ion in aqueous solution? Which one can easily break the bond and giving H plus ion in aqueous solution? That is H2T. See, H2T reducing character, I told you. Have a reducing character, it can easily break. The tellurium hydrogen bond can easily break and hydrogen can easily give. In aqueous solution, this bond can break to give H plus ion. So it is strong acid. So bond enthalpy decreases down the group. So acidic character increases down the group. Hydrogen telluride is a strong acid. Again, coming to reactivity towards oxygen. All these elements can form dioxides and trioxide. O3 is a dioxide of oxygen. Sulfur can form SO2. O3 and SO2 are gases. SCO2 is a solid. And SO2, SCO2, TU2. See, sulfur is in +4 oxidation state. I told you, lower members are stable in group oxidation state. Sulfur is a lower member of group 16 element. So sulfur is stable in +6 oxidation state. So +4 oxidation state of sulfur is converted to +6 oxidation state. That reaction is called oxidation. So sulfur dioxide can act as a reducing agent. Sulfur dioxide is a reducing agent. But as we move down the group, what will happen? Tellurium. Tellurium is stable in +4 oxidation state because of inert pair effect. So tellurium is stable in +4 oxide. It cannot go to +6 oxidation state. But it can reduce to any lower oxidation state. So tellurium dioxide can act as an oxidizing agent. So tellurium dioxide is an oxidizing agent, but sulfur dioxide is a reducing agent. So the sentence is written, reducing electron dioxide decreases from sulfur dioxide to tellurium dioxide. Then EO3 type oxide, sulfur trioxide, selenium trioxide, tellurium trioxide. All the types of oxides are acidic in nature. They dissolved in water, we get acid. SO2 dissolved in water, we get sulfurous acid. SO3 dissolved in water, we get sulfuric acid. So all the type of oxides are acidic in nature. Then coming to reactivity towards halogens. See, they will form 4 types of halides. Mainly hexahalides, tetrahalides, and dihalides. One more halide is that is monohalides. So hexahalide means they can form stable bond with the fluorine atom. Out of hexahalides, fluorides are more stable. Fluorides are more stable. Here there is a stability order of halides. Fluoride greater than, chloride greater than, bromide greater than, iodide. Small, fluorine is small sized. So it can form strong bond. So fluoride greater. So out of hexahalides, fluoride, out of hexahalides, tetrahalides, dihalides, fluorides are more stable. Then coming to hexahalide. Hexahalide, I told you the hexafluorides are stable. Sulfur hexafluoride, selenium hexafluoride, tellurium hexafluorides are more stable. And SF6 has an octahedral structure. SF6 has octahedral structure. Octahedral structure. Sulfur undergo sp3d2 hybridization. And it is highly stable molecule. It is historically stable molecule because sulfur is surrounded by 6 small sized fluorine atoms. See, so sulfur fluorine bond is highly stable. It is sterically stable molecule, highly stable molecule. All the bond angles and bond lengths are same. So it is highly stable molecule. Highly stable molecule. It is chemically inert. Okay. sp3d2 hybridization, octahedral structure, highly stable. Then coming to EX4, tetrahalides. Tetrahalides undergo sp3d hybridization. One lone pair is there, 4 bond pairs are there. So total 5 electron pairs, it can undergo sp3d hybridization. Having a seesaw shape, sulfur tetrafluoride. All electron pairs are arranged in a triagonal bipyramidal manner. Due to the LP-BP repulsion, these axial bonds are somewhat bent towards equatorial position. As a result, a seesaw shape, seesaw structure is obtained. So SF4, seesaw shape. SF4 is a gas. SCF4, selenium tetrafluoride, is a liquid and tellurium tetrafluoride is a solid. Again, dihalides. Dihalides. Dihalides na രണ്ട് bonds, രണ്ട് bond pairs இருக்கு, രണ്ട് lone pairs இருக்கு. இதே மாதிரி ஒரு molecule உங்களுக்கு நல்லாவே தெரியும், water molecule, H2O. H2O contains 2 bond pair, 2 lone pair. What is the shape of the molecule? Bend shape. You know, SCl2, SBr2, SeCl2, selenium dichloride, selenium dibromide. You know, oxygen cannot form dichloride dibromide. Oxygen can form O2F2 and OF2. Two fluorides can form, but others can form dichlorides or dibromides. The structure is bend structure. Bend structure. Then one more halides, that is monohalides. Monohalides. Monohalides, na, they are unstable because monohalide na one bond. So it has an unpaired electron, an odd molecule, monohalide. So they will undergo dimerization. The well-known monohalides are dimeric in nature. So we can write like this: S2Cl2, Es2Br2, Sc2Cl2, Sc2Br2, etc. These are the dimeric monohalides of group 16. And they are undergoing disproportionation. For example, selenium dichloride ScCl2, Sc2Cl2, on heating it undergo ScCl4 plus 3 Sc. Disproportionation, plus 1 oxidation state is oxidized to plus 4 and reduced to 0. Disproportion. So well-known monohalides are dimeric and it undergo disproportionation reaction. Group 17 elements, halogens. Group 15 elements are called nicogens. Group 16 elements are called chalcogens, and group 17 elements are called halogen. What do you mean by halogen? Halo means salt. Salt forming elements, halogens. Which are the members of halogens? Fluorine, chlorine, bromine, iodine, astatine, and tennessine. And this is the very important group for from this group, NEET examination question can be asked. Because after this, noble gas, this group has some importance. See, first one, valence electronic configuration. They have 7 valence electron, and this can be accommodated as NS2NP5. NS2NP5. If they accept one more electron, they acquire noble gas configuration. So they become more stable. They become anion, F minus, Cl minus, Br minus, I minus. So in all situations, in all chemical reaction, halogens are ready to accept one electron. Accepting one electron, gaining one electron means reduction. So they can act as good oxidizing agent also. Okay. So NS2NP5 is a valence electronic configuration of any halogen. Atomic radii. See, these elements have the smallest atomic radii along a period. Because along a period, the nuclear charge increases. So size decreases. So minimum size is for halogens in a period. Then ionization enthalpy. They are ready to accept one electron. So they will not give out any electron. So their ionized enthalpy is very, very high. Okay, very, very high ionized enthalpy. They will not give out electron. And coming to electron gain enthalpy, they have maximum tendency to accept an electron. So they release maximum energy during accepting of one electron. But one problem is there. Fluorine, chlorine. Compare பண்ணும்போது chlorine electron gain enthalpy is larger than fluorine. In the former group, chalcogens family, group 16 elements, oxygen electron gain enthalpy is lower than any members of the family because of small size. அதே மாதிரி இங்கேயும் ஒரு பிரச்சனை இருக்கு. fluorine, chlorine compare பண்ணும்போது fluorine size small. So electron வெடிக்கும் போது repulsion ஆயிடும். So large inter-electronic repulsion. So fluorine electron gain enthalpy lower than chlorine. Chlorine அதிகம் தான். Chlorine has large size. So the repulsion is less in chlorine after accepting an electron. So chlorine electron gain enthalpy greater than fluorine electron gain enthalpy greater than bromine electron gain enthalpy greater than iodine electron gain enthalpy. Then coming to electronegativity. These group elements are showing maximum electronegativity in a period. Fluorine is the most electronegative element, you know. Fluorine 4.0 is the electronegativity value according to Pauling scale. Then physical properties. Fluorine and chlorine are gases. Bromine is liquid. Bromine is a reddish brown colored liquid. And iodine is a solid. See, fluorine, chlorine are gases. Bromine is the only one non-metal in liquid state. Iodine is a solid. All halogens are colored. Fluorine is slightly yellow color. Chlorine has a greenish yellow color. Bromine is reddish brown. And iodine is violet color. Why they are colored? They are in native form, they are colored. At the same time, if they dissolved in any organic solvent, they will exhibit a different color. Why they are showing color? Only one reason for the color is excitation of electron from the valence shell. From valence shell, electrons are excited to higher energy level by absorbing radiation, and it is returned to its original shell by releasing the energy or color. That is the reason. Excitation and de-excitation of valence electron. And the solubility of fluorine, chlorine, bromine are react with water, and iodine slightly soluble in water, sparingly soluble in water. Okay. Then coming to bond dissociation enthalpy. That is very, very important feature of halogen. Bond dissociation enthalpy of fluorine is slower than chlorine and bromine. See, fluorine bond enthalpy is very, very less. What is the reason? Fluorine, small size. So there is larger interelectronic repulsion between non-bonding electrons. Large interelectronic repulsion. So this bond is highly unstable. Bond can easily break. So bond enthalpy of fluorine is lower than chlorine. Lower is fluorine greater than, bromine greater than, fluorine greater than iodine. Then coming to oxidation state. Fluorine being highly most electronegative element, it can exhibit only -1 oxidation state. But at the same time, other elements, fluorine, bromine, iodine, they have d orbit also, they can expand their valency and they exhibit, in addition to -1, +1, +3, +5, +7 oxidation state. Some elements show +2 and +4 oxidation state in their oxides. Okay. The oxidizing property of halogens. I already told you. They have 7 valence electrons. They are ready to accept 1 electron to form anionic species. And that process is reduction. So they can act as oxidizing agent. And their E naught value indicates E naught value positive means they can act as they can undergo reduction. They can act as cathode. So they are good oxidizing agent. And fluorine can oxidize even water. Fluorine can oxidize water. Chlorine and bromine can react with water. See, fluorine oxidize water to oxygen. At the same time, chlorine or bromine, X means chlorine or bromine. It react with water to form hydrohalic acid and hypohalous acid. If we are taking chlorine, Cl2, HCl, hydrochloric acid, and HOCl, hypochlorous acid will be formed. Iodine will not react with water. But iodide solution is keeping in atmosphere. It undergoes atmospheric oxidation to form iodine molecule. The anomalous behavior of fluorine. In a first member of each group show some anomalous behavior. I told you what are the reasons: small size, high electronegativity, high ionization enthalpy, absence of d orbital. In addition to this, 2 more points can be added for fluorine, that is low bond enthalpy. Easily bond can break, so it can highly react high reactivity. It can show high reactivity. In the high positive E naught value. Then some other examples of anomalous behavior. Most of the reactions of fluorine are highly exothermic. Most of the reactions of fluorine are highly exothermic. That means stable bond is formed. Stable and strong bond is formed by fluorine atom with any other element. Then it forms only one oxo acid, HOF, hypofluorous acid. But other elements can form oxo acids with oxidation number +1, +3, +5, +7. For example, chlorine, HClO, HClO2, HClO3, HClO4. But fluorine can form only one oxo acid. And HF is a liquid HF. hydrofluoric acid is a liquid because strong intermolecular hydrogen bonding. But HCl, HBr, HI are the gases. Then coming to reactivity, already we discussed about group 15, group 16, reactivity towards hydride. The same case here we can apply the stability. Down the group stability decreases. Hydrogen, fluorine, small size, so strong bond. Hydrogen, iodine, large size difference, bond enthalpy is less, bond can easily break, it can easily give hydrogen. So, HF, HI, least stable hydrogen halide, and reducing character, HI is the strongest reducing agent. HI is the strongest reducing agent. Then acidic character, HI is strongest acid because HF fluorine is the most electronegative element, but HF bond is strong. HI bond is weak, so it can easily liberate H plus ion in aqueous solution, so it is strong acid. BP and the MP, you can say that the abnormality of HF has high melting and boiling point, and because of the intermolecular hydrogen bonding. Then reactivity towards oxygen. See, fluorine can form OF2 and O2F2. They are called oxygen fluoride, not fluorine oxide, because fluorine is more electronegative than oxygen. So oxygen fluoride, not fluorine oxide. But other elements can form oxide, and the stability of the oxides of iodine greater than fluorine greater than bromine. Iodine oxygen bond is highly polar, high ionic character, so it is stability. And chlorine oxygen bond, chlorine can form multiple bond with oxygen, so stability will be higher. Bromine oxide, bromine has a middle row anomaly, anomalous behavior of middle member. Very good example is bromine. So bromine oxides are highly unstable. It exists at a low temperature. And chlorine can form Cl2O, ClO2, Cl2O6, Cl2O7, and they can act as oxidizing agent. And the ClO2 is used for bleaching purpose. Similarly, bromine can form Br2O, BrO2, BrO3, and they are least stable. They exist at a very low temperature. And iodine can form I2O4, I2O5, and the I2O7 oxides. And I2O5 can be used for estimation of carbon monoxide. I2O5 can react with carbon monoxide to form iodine plus 5CO2. This iodine can be estimated by titration. So carbon monoxide estimation, we can use I2O5. And halogen react with the metals to form their halides. Ionic halides are there, covalent halides are there. Higher halides are more covalent. Pentahalides are more covalent than trihalides. Adhe madri. Higher halide, metallic halides are more covalent than lower halides. Then halogen can react among themselves to form interhalogen compounds. XX- type, XX-3 type, XX-5, XX-7. Where X is a large sized atom, central atom, less electronegative. X- is small sized atom and highly electronegative atom. Fluorine cannot act as central atom in interhalogen compound because fluorine has only one valency. Fluorine highly electronegative, small size. Central atom should be large size and less electronegative and should contain d orbital. Okay. And the last group is group 18 elements. They are called noble gases, inert gas, unreactive gases. All are gases. And the members of the family are helium, neon, argon, krypton, xenon, radon, and organoson. Last member, 118th element, organoson. See, what are the general characteristics of this element? Valential electronic configuration is Ns2Np6. Ns2Np6. See, there is an exceptional case, helium. Helium do not have octet configuration. Helium has duplet configuration, 1s2. First shell is completely filled up without the 8 electron. Okay, no 8 electron is required and therefore it is duplet. Other elements are completed their valence shell by octet. Atomic radii. As we know that the other elements along a period atomic radii we are considering metallic and covalent radii, but in the case of inert gases we are considering van der Waals radii. because only one der Waals force is among them. And as we move down the group, van der Waals radius increases. Van der Waals radius value is very, very large. You studied in classification of elements. They have large size. Then ionized enthalpy, these elements have maximum ionized enthalpy in a period. Noble gases have maximum ionized enthalpy in a period. And the electron gain enthalpy, noble gas will not give out electron. I told you maximum ionized enthalpy. They will not accept electron. They have positive electron gain enthalpy. So will not accept electron, so they cannot undergo chemical reactions. Then coming to physical property, they are colorless gases, odorless gases, tasteless gases. They are slightly soluble in water, but the solubility increases down the group. Solubility increases down the group. They have very low boiling and melting point because only very weak force of attraction, very weak van der Waals force of attraction or London forces existing among them. See, helium. Helium was lowest boiling point of all known liquids. See, boiling point of 4.2 Kelvin. So helium was lowest boiling point because of very weak force of attraction. And helium has an abnormal property. Helium has a diffusing property through rubber, glasses, and plastics. Okay. So all these gases are monoatomic gases. Their Cp by Cv ratio is 1.66. It indicates that they are monoatomic in nature. And the chemical reactivity, they are least reactive, inert, unreactive gases. What is the reason for their low reactivity, inertness? What is the reason? There are two reasons. First one is their valence shell orbitals, S and P, are completely filled. NS2, NP6. Then second, completely filled. See, in the former cases, we studied p orbital is partially filled. So, it can undergo covalent bond formation. But here, all the orbitals are completely filled. That is first one. Stable configuration. Octet means stability. Stable configuration, completely filled S and P orbital. Second one, for in an atom to undergo chemical reaction to accept or electron or gain of accept electron or loss of electron. But both cannot happen in the case of noble gas. What is the reason? Because they have maximum ionized LP, positive electron gain enthalpy. So because of these two reasons, they cannot undergo any chemical reaction. But in 1962, scientist Neil Bartlett discovered a new compound of noble gases. That scientist first treated PTF6 with the O2 molecule. He got a red-colored compound. Similarly, again, instead of oxygen, he used a xenon gas. Again, he got the same red-colored compound, same colored compound. So, he found that some similarity between O2 and xenon. What is that similarity? The first ionization enthalpy of O2 and xenon are similar. First ionized enthalpy of O2 and xenon are similar. So, what is the energy required to remove electron from O2 molecule? The same energy can be given to xenon to react. So, xenon is then thereafter, there's produced a large number of xenon compounds, XCO3, XCF2, XCOF4, XCF6, etc. No chemical compounds of helium, neon, argon are known. Okay. Krypton form only one compound, KrF2. Radon form only one compound, which is identified by radio tracer technique, RnF2. And another one is uses of, the last topic is uses of noble gases. Due to its lightness and non-inflammability, helium is used in to fill the balloons, observation balloons, meteorological observation use பண்ற balloon helium fill பண்றாங்க. And helium is also used in artificial respiration. உங்களுக்கு தெரியும் பென்ஸ் டிசீஸ் பத்தி. பென்ஸ் அந்த பென்ஸ் டிசீஸ் அவாய்ட் பண்றதுக்காக respiration scuba divers in their cylinder, they are reducing the amount of nitrogen and increasing the amount of oxygen and also adding a little amount of helium. And the liquid helium is a superconductor. It is used as an essential component of NMR spectrometer and also MRI scanning machine. Neon is mainly used in discharge and fluorescent bulb. And argon is mainly used for providing inert atmosphere in metallurgical process to obtain metal. Okay, so these are the important points of P block elements. If you study, definitely you'll get a good mark from P block elements. See you, bye.